that they were so large, that, you know, in the range of 20 solar masses or so, because nobody had an idea of how stellar evolution could lead to such by itself could lead to such a massive black hole.
I think there's some. It seems that there's some controversy about that in the community. Some people say that this is very surprising, and some people say, "Oh, we've been saying this all along."
There's the pair instability supernovae that can make massive things like that.
That's right. Yeah, and I mean classical supernovae can as well. So for a very massive, you need to make a black hole of 20 solar masses. You need a star of more than 100 solar masses. But there are stars that are this incredibly massive. So the surprise would be sort of simply how many of them, perhaps, that we've seen.
Rick?
I mean, building on what Steve said, I thought the surprise would be that they thought the mechanism for a very stability supernova was pretty, that physics was pretty well known. And if you have massive stars, much more than 100 solar masses, the entire thing should disrupt. There shouldn't be any black hole left. And so that's what gives you the maximum size of a black hole. So it seems to me like the surprise would be, why is there not a pair instability mechanism that prevents large stellar-sized black holes? It seems like it might be easier to say those 50 solar mass or 30 solar mass black holes may have already merged with something else earlier.
I don't know the answer to that.
That's a good point.
So if those black holes form through the merger of other smaller black holes, they will have a higher effective spin. That is one of the things, and it wasn't the case. The other thing, for the pair instability gap, which is between 140 solar masses to 260 solar mass, roughly, it comes from the formation of a star, and it changes in the early universe compared to the now. Because at the moment, the universe, when they form a star, the average mass is 0.3 solar masses. Whereas in the early universe, because there are no metals, because there are no supernova explosions, so no heavy elements, meaning that nothing heavier than helium, they were, when they were collapsing, they couldn't cool down to lower temperatures, and the mass of a star that will form at the end of that collapse depends on the temperature to the 1.5. Because they couldn't cool down too much, they will become more massive. So you can explain this 100 solar mass stars forming, and at the end of their life, they will end up as a black hole. But there is a big debate on this. That is normally how we, at the back of the envelope, explain the star formation in the early universe compared to now. Because there's like a few hundred factor of difference in mass. So this is one thing. But that was for the primordial gas. Whereas even though now most of the stars that the universe is forming has 0.3 solar masses, the universe still forms 200 solar mass stars. We still have those. So for any given time, you can actually make massive stars, independent. I don't want to really say independent of metallicity, so the heavy elements, but there is more into forming a star than what we know now. It's very microchemistry that involves. We need to know how much of dust in that metals are, and what kind of dust, and what is the grain size distribution to end up with the mass of the star at the end. So it's very unknown territory. We are working hard on it, but we need more detections.
It's complicated.
I also want to point out that the physics of core collapse supernovae is incredibly, it's a major unsolved problem, essentially. It's incredibly hard. So people, you can make some arguments on pen and paper, but then you take those arguments and you put all the physics you know about into a supercomputer. You run this huge supercomputer simulation, and as far as we can tell, there's no consistency about the answer you get. You run this very expensive 2-month simulation on a huge supercomputer, and the star could explode, it could not explode, you could get a black hole, you could get a neutron star. Essentially, no one agrees on what should happen. Even you don't even agree with yourself. A past simulation will not match a present simulation based on the changes you've made to the physics you've included. So And yeah, the resolution is a huge question. So it's essentially, this is a major, major unsolved problem that the community has been working on for decades.
So is this a problem of equations of state of the kind of matter that you're dealing with?
So essentially, it's at the deepest level, it's a problem of computational power. At a sort of more surface level, it's a question of what physics you actually include. So essentially, we can't solve the problem accurately with all the physics because our computers are not powerful enough. So we cut corners somewhere. Various people cut corners in various different places and argue about where the corners deserve to be cut. And the result is that it seems everything is important because no one is getting the right answer.
Now there is also a possibility that the problem of core collapse and which star actually explodes and what it leaves behind could be stochastic in some sense and depend on sort of rotor turbulences as the star collapses. And it is possible that you take two exactly identical stars as they start their life, and one of them will have one kind of supernova explosion and the other one will have a different one. That's sort of a fairly new idea that has entered the field recently, but it's something that we cannot rule out at this point.
And that's sort of suggested by this inconsistency.
Yes.
I mean, you know, if the identical simulation produces different results, you know, round off error or whatever.
That's right.
Cosmic rays hitting the node of your computer. You know.
Yeah. Well, so it's definitely one thing is definitely true is the problem depends very sensitively on chaotic physics. It depends very sensitively on turbulence, and so. This is certainly another thing that makes it really hard.
Yes.
So I guess so gravitational radiation, I guess, is a prediction of Einstein's general relativity. Everything you've observed so far is in good agreement with that. Are there any possible discrepancies that you might be looking for? Is any other?
Yeah, absolutely. So there are a lot of things we've actually. I mean, a big success story of this whole gravitational wave detection has been careful checks on a lot of things we were looking for. So for example, you can imagine that gravitational waves actually propagate, they don't propagate at the speed of light, but instead they propagate at some other speed. Well, if we see light coming from the merger, say from a gamma ray burst, and we see the gravitational waves, then we can check that. We can also check if the gravitational wave, you might imagine, so associated with the gravitational waves is a particle, because associated with every wave is a particle. The gravitational waves, because they travel at the speed of light, their particle is massless. If they travel at some different speed that's less mass, that is less than the speed of light, then the particle will have some mass. And that means that the speed of the waves will depend on their frequency. And you can check that because that would mean that the waveform that's produced by the merger will spread out as it comes towards us, and that's called dispersion. And we can also look for that and check that, and we have, and it's been in exquisite agreement with GR. But that doesn't mean that that's the only thing that could possibly go wrong. I mean, in some sense, we know that GR has its limits because we can't combine it with other things we know about the universe, like quantum mechanics. And so I think one of the most promising ways at the moment of trying to understand how quantum mechanics and gravity should combine is by looking for how gravity might fail. And so there are other ways that we're looking for that. For example, you could imagine that black holes don't actually have an event horizon. There's like a firewall there, or the horizon is solid somehow, and you can look for this in the physical signatures of how black holes interact with their environment, or how light is lensed by a supermassive black hole, for example. So there's a project that's happening right now called the Event Horizon Telescope, which is essentially networking many radio telescopes around the Earth together to sort of form a much larger radio telescope in some sense. And they're using that to look at the black hole at the center of our galaxy and trying to image it. The black hole doesn't emit light, but it bends the light around it. And so what we should get is what's called a shadow of a black hole, where you see some of the light behind it gets bent in a particular pattern. Some light just doesn't escape, and you get a particular characteristic image.
I think either you or Aichin needs to explain what an event horizon is.
Okay, yes. The event horizon is the place of no return. Anything, if you're closer to the black hole than that, you can't escape, ever. And so that's why the black hole is dark, because everything closer to the center of the black hole than the event horizon falls in forever. And so that's what the event horizon is in a nutshell.
What's the shape of the event horizon?
So it's a bit like an ellipsoid, I guess. So essentially, actually, it's a lot like the surface of the Earth, right? The Earth would be a sphere, but it's spinning, so it sort of pancakes out a little bit. I'm going to wave my hands because there's actually no material at the event horizon, but the same sort of thing happens with the event horizon.
How about this recent merger? What would its event horizon look like?
Exactly the same. So after. So the neutron stars.
How squished would it be?
It's spinning
Compared
fairly.
to a sphere.
So this one, because it came from the orbit of two stars, it has a lot of angular momentum. So this black hole is actually spinning sort of rapidly. It's not spinning as rapidly as the previous black holes we measured from other mergers, but it's sort of, so it's not a huge effect, but it is certainly, it's pancaked because it's spinning fairly rapidly.
One interesting thing to point out, though, is that the shadow doesn't look like...
The shadow does not look like a pancake,
so
no.
if you see an image of a shadow, it's actually flat on one, like if this black hole is spinning rapidly, it's flat on one side and sort of ellipsoidal on the other side, and that's because the light gets bent around in such a way that it makes one side look smaller and flat because the way that the black hole spins.
So you can tell which way it's spinning.
Yes,
you can. Yes,
if you could actually observe the shadow, which we might with the event horizon telescope.
Because on a planet or a star or something, the shape of it doesn't tell you which direction it's spinning.
Right.
That's quite interesting.
Yeah, but with the black hole, it's because it's not just the black hole that spins, but it's space around the black hole that is sort of dragged along with the spin of the black hole.
So the photons that are passing by the black hole essentially get pulled by its rotation.
I'd like to see that.
There's images on the web, like simulated images.
Simulated images. I'd like to see it for real.
Well, in Interstellar, the image you see is not accurate with what the black hole should be. And that's because the director thought it was too complicated to explain to the audience why one side should be flat, and so they
simulated a non-spinning black hole.
Well, it was like a spin of 0.6 or something.
Yeah.
But it should be spinning at like 0.99999.
Yeah.
Guess I should see that.
Questions over here.
I have two related experimental questions. So you've alluded to it a little bit, but what is the time scale of the observation of the 2017 event specifically? And then secondly, related to that, based on our location in the galaxy and other bodies of interest to look at, where does it, at least on the Earth, make more sense to locate additional observatories? Geopolitical chaos, notwithstanding.
Yeah, so I'll answer the second one first because it's easier. The universe. So we don't expect most of our in fact, of our observations for binary mergers to come from within our galaxy. The rate is just very low, but we can see so far. We can see so many galaxies that we can get an answer, or we can get a reasonable rate. So it actually does. The direction of over the Earth doesn't matter at all, because if you go sufficiently far away from the Earth, modulo some weirdness, all directions should be the same.
So what does matter, though, is we want to have a network of observations, like sort of evenly spaced around the Earth. So
because we don't want blind spots.
Exactly.
Right. Your first question is actually very complicated because it depends on the kind of stuff that we detect. So the actual, the gravitational wave signal was tens of seconds.
For the neutron star merger.
For the neutron star merger. For a black hole merger, it's less than a second, because the black holes are heavier, and so they spin fast. They orbit each other faster. The gamma ray burst, also of order seconds. Then the other stuff, as Jonas alluded, the radioactive decay is of the order of a week or more. And then there's also material that was thrown off that's expanding. And this material is also glowing for other reasons. It's just because it's moving quickly. And that's called the afterglow of a gamma ray burst. That can be months. So it's basically all time scales. I mean, we expect to observe this thing for years to try and understand sort of the aftermath of this event.
So actually, so it happened in August. We are still getting data from it,
Right.
and especially in X-ray and radio. And some of the radio emission actually comes from the fact that you have this material that is expanding very rapidly, and space is vacuum to a very high degree, but it's not a complete vacuum. So as that material sort of slams into the very, very dilute material that's just between stars, it creates additional radio emission, and we're still seeing that.
But it's the key that first, if the gravity wave detection is kind of the key to turn all the other detectors to a particular location.
Yeah.
It makes it that much more important.
So, yeah, that is one of the major. That was a major goal of the network when it was being proposed, is that it can be used as a tool to help other kinds of astronomers point their telescopes at the right place in the sky. And you know, in this case, the story is a little bit weird because the people who noticed it first were actually the gamma ray burst people, but they couldn't localize it. So the key, certainly in this detection, the key piece of the story that gravitational waves provided was the position.
So some of the signal the gamma ray burst preceded.
It didn't precede it. It's just that the essentially the gravitational wave people ignored their data because there was one of the detectors was shut down at the time, and there was interference in it, and so they were they're very careful. They don't want to send out false alerts.
Right.
So they were not confident enough in their signal to say anything until the gamma ray people said, "Hey, we saw something."
And also, the data that the gravitational wave, like that LIGO is collecting, it takes time to analyze.
Right.
And so once the signal of a gravitational wave actually goes through, it's a few minutes before the software that's continuously analyzing the data and cleaning it up and doing the matching between the two detectors will actually tell us, or will tell LIGO that something happened. And then an automatic alert gets set out to other observatories, and then people go in and try and analyze the data and try to figure out where it happened. And so this whole process of analyzing everything takes a few hours until we, yeah.
It's being streamlined.
Yes. Yeah.
But and it took especially long this time because there was interference in one of the detectors. So I think the previous latencies were not of the order 12 hours. They were of the order like.
Well, okay. So the 12-hour was a different reason. There was